Today we're setting a graph on fire, and as the graph burns, we will see the whole process and the order of the nodes getting set on fire. And the most exciting part is this is exactly how the breadth first search algorithm works. So in this video, we will go over the intuition behind the breadth first search algorithm, we will implement it in Python, and burn down many different graphs to see how it actually works. But before moving forward, what do we mean when we say graph? Well, basically, any connection of nodes which are drawn as circles and edges that connect those nodes can be considered a graph. So this is a graph, this is a graph, this is also a graph, and this is a directed graph as the connections between nodes are directed. Graphs are very popular in many applications. Representing your followers and friends on social media can be done through graphs. Web scrapers represent web pages as nodes, and links between them are the edges that connect those nodes. Finding the shortest path from one place to another is a classical graph problem. So in many cases, we might want to traverse the graph to observe some properties, search for a node, or see if the graph is connected. And one of the most common ways of doing it is with breadth first search, or BFS for short. Let's say we have this graph and would like to list all the nodes that are reachable from the starting node 7. With breadth first search, we would start by setting the starting node on fire and watch that fire spread to its neighbors. When the neighbors start burning, the fire moves to their neighbors, and in several iterations, all the connected nodes in the graph burn, indicating that we have visited them and they are reachable from the starting node. When there are no more new nodes to burn, we can confidently say that all the nodes that have been set on fire are the nodes that are accessible from the starting node 7. And the great news is this is exactly how we will implement the algorithm. And to do that, we will need to keep track of three things. First, we will need to keep track of the state of a node. Is it untouched or already burning? Second, we will need to keep track of the currently burning nodes that haven't passed the flame to their neighbors yet. And finally, we will need to store the graph itself. Let's start with the last one. As we represent the graph as enumerated nodes that are connected to each other, it's the most convenient for this case to represent it as a two-dimensional list, where each index represents the node number and the content at that index is a list with all the neighbors that the node is connected to. Let's call it G as a shorthand for graph. For the node at index 0, we will have only the number 2. For the node at index 7, we will have a list with 5 and 6 in it. For the node 8, we will have a list with values 4, 5, 9, and 10. Notice when two nodes are connected, we have their numbers in both lists. This indicates that we can reach from node A to node B and vice versa. Try to pause the video and think how we would store the lists if the graph was directed and we could only move from node A to node B, but not in the opposite direction. Now let's go back to the first and second things that we need to keep track of. We need to know whether each node is burning or hasn't been touched by the fire yet. To do that, we can store an array with Boolean values matching the size of the graph. Let's call it used. As none of the nodes are set on fire initially, all the values in the used array can be set to false. If a node starts burning, we will set the value at the corresponding index to true. So when we set the node 7 on fire, we will set the value of used 7 to true. The last thing we need to keep track of is the collection of nodes that are currently burning but haven't passed their fire to their neighbors. A very important thing that we want here is to keep them in order of when they started burning. This is important as the sooner the node starts burning, the sooner its neighbors should start burning too. So we should have a queue of nodes that are currently burning. When a node starts burning, we can add it to the end of the queue, and when the node spreads fire to its neighbors, we can remove it from the front of the queue as it's not going to do anything from that point on. In Python, we can use the DAG from collections to store the queue of nodes that are burning but haven't set their neighbors on fire yet. DAG allows to append elements to the end of the queue and pop elements from the front, which is exactly what we need. Having all of this, let's put it all together and implement the BFS algorithm. We will first store the graph in a 2D list, after which we will initialize the used array to be filled with false values and have the same length as the graph itself. After this, we can set node 7 on fire, so we will mark used 7 as true and will initialize the queue of nodes that are burning but haven't spread the fire to their neighbors yet with the initial node 7. Now the fire can start spreading. While there are still nodes that are burning or while the queue is not empty, we will take the front element of the queue and set all of its neighbors on fire. So we will loop through all the neighbors, and if the neighbor isn't used yet, we will add that neighbor to the queue and mark it as used, indicating that it's already burning. This ensures that we don't add the same node to the queue several times. In the end, all the neighbors where the used value is set to true are the ones that have been reachable from the starting node, so we can print their numbers. Let's simulate the algorithm on this graph to get a better intuition of how each part works. After setting node 7 on fire, we will enter the while loop. We will take the node 7 from the front of the queue and iterate over its neighbors. We will first add 5 to the queue as it hasn't been touched before and mark it as used, after which we will add node 6 and mark it as used as well. In the next step, we will take node 5 as it's at the front of the queue. We will then add node 3 to the queue, then node 4 and 8, after which we will skip node 6 and 7 as they have already been used before and we cannot burn a node twice. During the next step of the while loop, we will take 6 from the front of the queue and add 10 to the queue while skipping node 7. Moving on to the next node, we will try to process node 3, and as it's only connected to node 5, which has already been burned before, we won't do anything. The next iteration will process node 4. We will add node 9 to the queue and burn it while skipping nodes 8 and 5 as they have already been used before. In the next step, we will process node 8. As all of the neighbors of node 8 have already been used, we won't do anything, so the queue won't be modified. Next, we will take node 10 and after skipping the neighbors 8 and 6, we will add node 11 to the queue. The next step of the while loop will take 9 and after skipping the neighbors 4 and 8, we will add 2 to the queue. As 11 is not connected to any node that hasn't been touched before, the fire on that side of the graph will stop propagating. In the following step, we will take node 2 and will burn nodes 0 and 1 while skipping node 9. After that, we will take node 0 and as it's connected to node 2, we won't do anything. Finally, we will take node 1 and as it's also connected to node 2, we won't do anything, which will stop the fire from propagating and empty the queue. At this point, the BFS algorithm stops and we can iterate over all the neighbors to see which ones weren't touched by the process. If the node wasn't used in this process, it means that there was no path connecting node 7 to that node. So we can conclude that nodes 12, 13, 14, 15, and 16 were not reachable from node 7. The great thing about BFS is that it can be applied to a wide range of problems. One of the most commonly occurring sets of problems is finding properties on grids. Imagine having a grid where each cell can be either part of a land or the ocean, and we would like to know the number of islands on that grid. We consider that a piece of land is connected to each other if the cells are neighbors in horizontal or vertical directions. At first glance, this might not feel like a problem that can be solved with breadth-first search, but it actually has a very elegant solution using BFS. Instead of nodes and edges, we will be working directly with the cells of the grid. We can go through all the cells of the grid, and if we come across a piece of land that hasn't been touched before, we can start a fire from that cell, which will ensure that all the cells that are part of that island will get burned. We will then continue to go through the cells of the grid and start a fire as soon as we find a cell that is a land and hasn't been used before. So we will first initialize the grid as an array of strings, each one representing one line of the grid. After that, we will initialize the used list, which would be a two-dimensional list representing whether we have visited each cell or not. After which we can create a variable islands and set its initial value to 0. It will be used to count the number of islands we've encountered so far. We will then loop through all the cells, and if a cell is an island and is not used so far, we will start a fire from that cell and increment the count of islands. When implementing the BFS function, we will operate on the grid directly. So having the starting coordinates row and column, we will mark those coordinates as used and initialize the queue with the starting coordinates. As long as the queue is not empty, we will take the frontmost coordinate and try to move in the 4 neighbor directions. To move up, we will check if r-1 is within the bounds of the grid, as well as if it's a land and it's not used before. If that's the case, we will mark it as used and add r-1c coordinates to the queue. After that, we can do the same thing for the down direction. Having done that, we can implement the same logic for the left and the right directions. You can pause the video and try to think what the implementation would be like if we could move in diagonal directions as well. How many conditions would we need to do that? If you figure that out, try to think of a way to reduce the amount of boilerplate code with additional for loops. Okay, having this implementation, let's run it on the given grid and see how it actually works. We will first initialize the used two-dimensional list with false values. After that, the islands counter will be set to 0. Starting with the next step, we will iterate over the rows of the grid. On each iteration, we will look through all the cells within the current row. So we will go over the columns one by one and check if the value is part of a land. As soon as we find one that hasn't been used before, we will start BFS from that coordinate. So we will call the BFS function from coordinate 0, 8. The BFS function will set the value of used at 0, 8 to true and initialize the queue with the starting coordinates. After entering the while loop, we will take the value of the initial coordinate and check all 4 neighbors to spread far to those. After adding the bottom one to the queue, we will go back to the start of the while loop. Taking the next coordinate, we will check all 4 neighbors and add the 2 ones on the sides. During the next 2 iterations, we will take the front of the queue but not add any elements to the queue as there aren't any available ones. This way we will know for sure that all the cells in the first island are burned down. So we will move on to continue looping through the grid until we find the next cell which is part of an island and hasn't been used before. As we come across the coordinates 1, 1, we will start a fire right there by calling the BFS function on the coordinates 1, 1. As we enter the function, we will set the used value to true and initialize the queue with those coordinates. In the while loop, we will check all 4 neighbors of the initial coordinate and add 2 of those neighbors to the queue. After that, the next 2 iterations will pop the front elements from the queue and add nothing back as there are no more cells in this island to burn. Having the second island processed, we will move back to going through the for loops in search of untouched island cells. The search will continue until we reach the cell 36. As soon as we reach it, we will set it on fire and the BFS function will start checking the neighbor cells. We will add the cells to the right and to the bottom of the initial cell. After that, the fire will expand to all their neighbors and the process will continue until there are no more cells left on this large island. After the while loop is stopped, we will return to the loops that go through all the rows and columns and will try to find the next uncharted territory. This process will continue until we hit the cell 51. The BFS function for this one will be pretty short as it will only process one cell and will stop working almost right away. The next island starts at 60, so the BFS function will start processing it. Yet, again, it will stop right there as there are no neighbor cells that we can add to the queue. So this way we found all the islands and explored all of them. We can confidently say that there are 5 islands on the grid. Probably the most common application of breadth-first search algorithm is finding the shortest path from one node to other nodes in the graph. As we set the graph on fire, we can track the time each node was set on fire. This way, we will be able to understand how long it takes to get from the starting node in the graph to any other node. Imagine we're given this maze where the dots represent the free path and the hashtag symbols are the walls. How can we change the BFS implementation to find the shortest path from the starting coordinate to the final exit coordinate? You can pause the video and try coming up with an implementation yourself. When we try to find the shortest path in a graph, one good way to think about setting the graph on fire is to imagine that each node burns for 1 minute, after which the fire spreads to its neighbors almost instantly. So we would be interested in the number of minutes the fire takes to reach each cell, and to do that we can get rid of the used list and instead track the number of minutes or the distance from the starting position to that cell. Let's call the distance list D and fill it with -1s initially to indicate that we haven't reached any of the cells. -1 in D is the same as the false value for used. Okay, so to start the fire, we will set the value of the starting coordinate to 0. After that, when the fire spreads to the neighbors, we will set the value of the neighbors to the value of the current cell plus 1. Now let's implement the BFS algorithm on this grid to find the length of the shortest path. We will initialize the grid and fill the 2-dimensional list of distances with -1s. After that, we can set the value of the starting coordinate to 0 and add it to the queue. The only difference in the while loop of the BFS algorithm is the change from used to the distance list D. We will take the front coordinate from the queue and start checking for the 4 neighbors. If the neighbor coordinate is within the bounds of the grid, it's part of a path, not a wall, and it hasn't been visited yet, we'll set its value to the current cell's value plus 1 and add it to the queue. The same process will be repeated for all the 4 neighbors. So on the first iteration of the while loop, we will take the starting coordinates from the queue. We will check the 4 directions one by one and add the ones that are within the bounds of the grid and are not walls to the queue while also updating the distance list. In the next iteration, we will take the front element of the queue and repeat the process of checking all 4 neighbors. You can notice that each cell is visited only once, and because the BFS algorithm burns the graph in order, the distance is always the shortest. You can think of the value in each cell as the number of minutes it took for the fire to reach that cell. The process of adding cell coordinates to the queue and gradually burning all the reachable cells in the graph will continue until there are no more cells left to burn. Let's analyze the time and memory complexity of the BFS algorithm. Say there are V vertices and E edges in the graph. As we check for each vertex to not be used before adding it to the queue, we can know for sure that we only add each vertex to the queue once. When looking for the neighbors, we touch each edge at most twice. Once when going from vertex A to vertex B, and once when checking if A is already used when we are at vertex B. This results in a total time complexity being O of V plus E. In terms of memory complexity, we store the graph as an adjacency list that has E elements in total, representing the edges. We store the used array which has V elements, and the queue can have at most all the vertices of the graph at any point, which is also V elements. So in total, the space complexity is O of V plus E. Many problems disguise themselves and might not seem like the BFS algorithm can be applied to solve those. Some might seem like math problems asking you to get from one number to another with arithmetic operations using as few iterations as possible. This can be modeled as a BFS problem that finds the shortest path between two numbers. Others might involve modeling the use state as a 3D or 4D space instead of just a grid or just a list corresponding to each node in the graph. There are many tips and tricks when it comes to BFS, like starting the var from multiple sources at once instead of just one, and the intuition of when to use those comes with a lot of practice. So be prepared to use the breadth first search algorithm in many interesting places, and to better understand the BFS algorithm and develop a better intuition of how it works and which problems can be actually solved with breadth first search, try solving several hands-on problems. I'll leave some links to exercises to practice the breadth first search algorithm and different graph representation techniques in the description. So this was it for the BFS algorithm. Don't forget to like this video if you found it helpful, subscribe to see more tutorials like this. Thanks for watching, and I will see you in the next one.